started with telling you about nanojunctions. It's a small startup in northern Kentucky. So if you are familiar with the United States geography, this is the West Coast. So you can see Washington over here. New York will be over here. And then Cincinnati is in the Midwest. So there is a river called the Ohio River. And I collaborated with the University of Cincinnati, and also I was a professor at the University of Northern Kentucky University, which is located around this area. So a nanojunction is located along the Lincoln River in the Covington city. So over the years, I had collaborated with my former advisor, which is David Mast. And this is some of the students. We had a technician, Terry Craftman, who was very knowledgeable in everything that we did. And these are the students that we worked with in the summer of 2018. After that, in 2019, I carried out my investigations at the Brookhaven National Laboratory. But what I will tell you today, it was actually carrying on this lab as I was a graduate student. So let me tell you a little bit about Josephson Junction. I didn't think any talks were on that. So a Josephson Junction is basically a sandwich made with two superconductors where you can have an insulator in between, or you can substitute that insulator by a normal matter, a weaker superconductor, or even a semiconductor. And then you have a tunnel between the two superconducting islands. So this is a survey of different types of structures that show the the Josephson effect. Today I will describe a type of S-N-S junction, and also another type which we haven't classified yet, but we are trying to name it some type of magnetically weakened Josephson link. So basically, during my studies at the University of Cincinnati, I compared the electrical behavior of two systems. One was a classical S-N-S Josephson junction array. In this case, you can see this structure here is a rectangular shape with a gold underlayer, and this is supposed to be gold. And then there are some black crosses, and this is made of niobium. So from center to center, the niobium islands or crosses are distributed at 10 micrometers. And there is a gap in between, which is between 0.3 and 0.5 micrometers. So there would be a Josephson effect tunneling through one island to the next through the gold underlayer. The other structure, the ones that I focus on the study, which gives us a lot of insight, is a niobium film which was grown on top of an array of nickel dots. So the dots, this is a picture. This is too big. You cannot see the dots. But they are 200 nanometers in diameter. They are spaced center to center by 400 nanometers. And they are itself grown on a substrate, and they are 40 nanometers thick. The film itself is grown on top and is 65 nanometers thick. And then there are some leads where we can pass the current from one side to the other, measure the transversal voltage, measure also the longitudinal voltage. In the case of the array, we do the same. We have these string leads here to send the current, and then we measure the voltage using the 4-probe method. So to do these measurements, we developed this special type. It's a helium cryostat, which had the advantage to be able to control the temperature very accurately. We were in the sub millikelvin control and stability. So this was very, very useful to see the type of effects that I will show you in a minute. So we have a cell where we will connect our samples. And then there are filters that we can send our DC signals, and also we can couple our samples with some RF signals in and out. And so we did a complete study of as a function of magnetic field, temperature, resistivity, and apply radio frequencies into the two systems that I showed you before. Okay, and we created a customized data acquisition program made with LabVIEW to do this measurement. So this was a little bit complicated, but it gave us the ability to, at the same time, at the moment that we were taking the measurements, we could visualize what we were obtaining, and if we were maybe missing the temperature range or the magnetic field range, we could make adjustments on the fly. So this is what we obtained. I'm showing you here the resistor transition of one of the S-N-S arrays. So in this case, there are 300 crosses along the current direction and 50 crosses in the perpendicular direction. These designations are, this is just like when was the measurement taken. So you can see here, this was one measurement we took in 97. And what you see is that after the TC for niobium was in this case about 9.2 kelvins. So once we go below the TC, then we have a rapid reduce of the resistivity. This is due to the transition of each one of the islands, but still there is the goal, which is not superconducting, and then we have to continue lowering the temperature of the sample past this proximity effect region until we can have a complete superconducting. And in this case, it was about 3.2 Kelvin, so we had to pump on the helium-4 system to achieve to get to this point. But here, every measurement, you can see the resistance error bars. So it was a very stable system to do this measurement. Now, in the case of the niobium film on top of the nickel square sample, we said something very, very much more classic. So we have above for niobium. In this case, we have above 7 kelvins. This is because of all the processing that we have to do on the system. So there is a reduction of critical temperature. But then not so sharp of a transition. And finally, we get to a region where the resistivity is zero. The resistance of the sample is zero. But what I'd like you to pay attention here, there is a region here that is not quite zero. And this was puzzling for me. So when I zoomed into this region, I noticed that there was a minimum here, but then it will increase again to a maximum point, and then it will go down again. So it will kind of behave like the array. So I was not looking for this effect when I measured these samples. I was trying to reproduce the results that actually Professor Ivan Schuller from the University of San Diego, who created the samples, had observed. So my claim or my discussion with them was that maybe in their case, they didn't have such a stable system as I have, because there was a continuous flow system, and in my case was a helium bath. So maybe they didn't observe this, but we actually could never go to a resolution on the issue. But the fact that I have this increase in resistance in the sample, it gave me insights of other things. But so let me show you before I continue what I think it happened in the sample. So this is my visualization. It's a caricature of what I think it was happening as I lowered the temperature. So every square of this, I mean, what you see here at the background is the substrate. Then every circle here is one of the nickel dots. And then there was a film on top. And I'm emphasizing that at some point the film stopped. If I can go back to the the drawing or the picture of my sample. So, I will assume that I'm showing you a region like this. So the nickel dot is grown on top of the substrate, and at some point, the niobium film cuts some of the nickel dots at some point. So this is what I would see with the picture, but my imagination will tell me that it will look something like this. So what is happening as a function of temperature? So as the temperature decreases, then there will be a region which is fully superconducting. That is represented by the dark blue area. So that region that is superconducting is the one that produces this drop. It's the majority of the area that is covering the film. So the current goes through here. But then there will be a region around each one of the dots, which is, it has a weaker superconductivity. And that is what I see over here. So there are some effects which I cannot describe all of them. We didn't go into a comprehensive measurement on all the possible effects that we have here, all the possible parameters of the experiment that could influence the results. For example, I told you that the thickness of each dot is 45 nanometers, but the thickness of the film was 65 nanometers. So if we were to look at these films on the side, you might see maybe there is a modulation on the film. So definitely there is a non-equilibrium superconductivity effect that occurs that we can account that might explain what this is happening. But then, eventually, the other feature I wanted to do is that there is these diamonds, blue diamonds. So on the intersection between interplaces between 4 dots, there will be a stronger superconductivity at any particular temperature. Eventually, as the temperature continues going down, the whole film will be completely superconductor. So if you look at this picture and then you compare it to an array, which is over here, so this is a simplification of the array that I showed earlier. Each one of the crosses represents, the black crosses represent the niobium film on top of the gold. I could draw a simulation of an overlay between the two. So the hypothesis that we have is, or was, could this niobium film over nickel dots somewhat behave at a certain temperature as an array of Josephson junctions? So that is the picture I'd like you to keep in mind once we see the next pictures. So this is what the voltage current characteristics for this particular S-N-S Josephson junction array. This is done at a fixed temperature. In this case, you can see I have 5 significant figures. So I go to hundreds of millikelvin of microkelvin of stability in the system. And you can see the error bars here, but they're really so small. So I take an IV with the system that I showed you before using the data acquisition, and then I take the dynamic resistance. So I see a couple of features here. There is a maximum around this region. I will define this as my critical current, and then I can see that below certain value, the resistivity is 0. So this similar behavior will have it for the niobium over the nickel film, the nickel dots array. In this case, I'm plotting on the red lines the temperature of the sample thermometer. The sample thermometer was a thermometer which was very close to the sample, so it could register anything that happened to the sample. The sample thermometer was able to register, and you can see the error bars here for the temperature there. It was very accurate. So again, voltage current characteristics, I will define as a fit the normal resistance at this region here. And then again, when I take the dynamic resistance, I will see some features. And in this case, I would define, I would use another definition for the critical current. So far, so good. The systems are behaving similarly. I'd like to point out here that I am measuring the temperature at 7.8, the sample temperature at 7.8 kelvins. And if I go back to, sorry, not that way. If I go back, this is sample temperature. So I was measuring the IV somewhere in this region where the sample is not fully superconducting. So it is in a region that looks like this. So I placed myself somewhere around this region, and I did all the measurements that I'm showing you. So in this case was 7.8 kelvins. So the next thing that I did was I apply a radio frequency signal. So in this case, I applied the frequency for the signal that superimposed was 50 megahertz. And if I plot, I plot the voltage now in the x-axis and the current in the x-axis and the voltage in the y-axis, and I normalize it by the voltage that will satisfy the Shapiro step equations, which is given by this equation over here. Then I will see that this black curve is the previous one that I showed you before, but when I apply a radio frequency current superimposed to the sample, in this case of this magnitude, there will be these very sharp steps formed, and they would correspond to the values given by this equation. So this is just a classical behavior for a Josephson junction array under the influence of radio frequencies. But we did the same thing for the nickel over niobium over nickel sample. And yeah, I don't see anything in this case. There is a considerable AC current, but I won't be able to see this Shapiro step so easily. In here, I'm showing you on the red curve here is the sample temperature. So again, I just put it there to give you a sense of how stable was the sample during the measurement. The temperature of the sample during the measurement, which is important sometimes. There would be, since there is a resistance, there would be a considerable amount of self-heating. And we will see that later on as we increase the power of the RS signal that we're applying there. But if I take on the same curve, if I invert it again, so voltage here in the x-axis, current in the y-axis, but now I take the dynamic resistance and I plotted that, I will see that at the points where the Shapiro steps occur, there will be some minimum. Now, so I take the same curve that I showed before, then I will see the minimum. So only by using the dynamic resistance measurement was when I was able to see that there might be some steps there. So I labeled those steps, and I did the classical analysis to see if this system could be considered to be a type of S-N-S junction, just S-N-S array. So as we applied different values for the critical current, so I'm plotting here the strength of the radio frequency current superimposed to the RBs, and then I'm plotting here. I take the first the width of the first step. So the first current step in the previous graph would be this distance between the bottom of this step to the other one. So I would measure that by some method, and then I would plot this would be the strength of the first step, of the second step, and so on. and I will plot that as a function of, so this would be the strength as a function of the strength of the magnetic of the applied relative to the current. Then I will see a classical behavior, and then so this would be the behavior for the first step, which is the critical current, and this would be the behavior for the first step, and so on. Depending upon how similar each one of the junctions, we will see more steps being formed. But after there's some randomness and in any type of randomness on the array, then these functions will know they will wash out. And this is what we see over here. So here I'm plotting the first step, but actually the critical current in black, and then as I increase the amplitude of the AC signal, the RF signal that I'm applying on the sample, you can see how the sample temperature starts heating up and increases. But nevertheless, we are still very stable. We are, even though there is some heating effect, this is in the order of millikelvins. So go from 7.08 0880 to 8130 over here. So it's not much. If some of you are experimentalists and have done this type of measurements, most of the time, most equipments, they don't give it such a stability. So and also I can not only notice that the sample is heating up, but also I have the error bars that can indicate these are the error bars for the temperature at the sample. So in this case, I will see that there will be an increase in the critical current up to some maximum, and then it will be completely washed out as the RF signal increases. So we'll see none of the oscillations that we see for the case of the steps. Let me see what time I have. Okay. Then again, I plot this maximum. I normalize it as a function of the resistance. And this would be, again, another classical behavior for a Josephson junction array. So this is sort of the steps versus the RF frequency. But for the nickel, the niobium of the nickel sample, the only thing that I could say was that this maximum follow a behavior given by this equation. And this was the only indication that we could have that in fact, we were having a Josephson junction array type in these samples. The next study, we vary the magnetic field in the sample. And then for the array, the S-N-S array, we see a strong modulation as a function of magnetic field that will follow this equation. So we satisfy the flux quantum equation. And for the niobium over nickel array, we determined that this was the first minimum, and then we resolved by using the value of the quantum flux. We resolved that in fact we were having a modulation with magnetic field which correspond to the area of one of the in this case the 200 by 200 nanometer area for the case of the niobium nickel sample. And So in this case, that area will be here. For the S-N-S sample will be 10 micrometers square, and for the case of the nickel, the niobium nickel sample will be 200 by 200 nanometers. Okay, so after this study, I took off the idea that I could have an increase of resistance by combining a magnetic material with a superconducting material, and I joined the group of Professor Maeda at the University of Tokyo under the project of we were intending to fabricate high temperature superconducting Josephson junctions for SFQ circuits. And our contribution to the group was in the creation of a type of Josephson junction with high TC materials. To carry this study, we created this a new probe. So in this case, we study lanthanum, strontium, copper oxide superconductors. So we needed a probe that will be able to be controlled between 100 kelvins and 4 kelvins. We had a small magnetic field that we could apply up to 350 Gauss made with the superconducting wire. And we could apply a microwave signal up to 20 gigahertz by using this the end of this waveguide over here. So this probe was inserted directly into a helium-4 cryostat, and the control was done similarly to what I showed you for the previous study. Okay, so what we conceived in this case was to make a type of a bridge. So in this sample, I show you here, there is a bridge in between that you cannot see, but the bridges have different width. So 400 nanometers, 300 nanometers, 100 nanometers, and 200 nanometers. And then you see the substrate here is LSCO, and then the film was LASCO. And then we place a magnetic strip on top of each one of the bridges. So actually the numbers given here is the width of the magnetic strips. So in between each one of these bridges, we have another sample that had no magnetic material deposited on top. Okay, so here I'm showing you the resistance transition between a sample that has no magnetic material. In this case, we use iron, and with what happened with the resistance transition of a sample that has iron deposited on top. Okay, so what we see here is that there is, for the sample that has iron, which are the ones here in the middle, so 300, 400, 200, and so on. In this case, I'm showing you the result for the sample that has an iron strip of 300 nanometers in width. For this sample, we can see that there is a somewhat reduction of critical temperature. So the virgin sample, the lanthanum structure copper oxide virgin sample, has a TC of around 28 kelvins, but when we add the iron, then we'll have a reduction on this critical temperature. And also there is an increase in the normal resistance of the sample. So by combining this magnetic material, in this case iron, with or deposit that on top of the superconducting material, we not only reduce the critical temperature, but also increase what we call the normal resistance. So the origin of that, I will explain that later. But what we notice is that if we zoom into this area over here, is that, again, this behavior somewhat is related to what I observed in the previous study for the niobium over gold or niobium over nickel. So there is a region here that can be distinguished between a superconductor that has no vicinity with any magnetic material, and a superconductor that, in this case, the magnetic material is right on top of it. Then, at some temperature, in this case, I place myself at 15 Kelvin, so it's way down here into where both systems are fully superconductor. And if I compare the resistive transition, or sorry, the resistive voltage curves for both systems, the one with the iron in red and the one without, then you'll see that there is a reduction on critical current compared to the virgin film, and also if I take the value of the resistance way after this has normalized, and I multiply this value of this resistance by the critical current that I obtain in this case, then I would have what we call the ICRN product, which is pretty high, and this is very important for applications. So we are actually this is one of our goals. We wanted to be able to create Josephson junctions, or in this case, weak links, with a high ICRN product. So we were very excited at seeing this, and then I would like to explain to you what is the concept. So what is this LSCO microbridge with a strip of iron on top? So basically, this is the microbridge, and then we place a particular a particle, a microdot. So to make the relationship between this study and what I showed you before we have the substrate and we have the nickel on top of the substrate and the superconductor on top. In this case, we inverted all of that because, as you know, it's very difficult to work with high TC materials. So it's easier to grow the best film that we can make on top of the substrate, and then on top of that grow the magnetic material. So we thought that inverting the order of the process won't change. So here the width of the magnetic material is this. The length of the magnetic material, the strip, what we call the strip, can be larger as the width of the bridge. And so this would be WS, would be the width for the superconducting section. This would be the thickness of the magnetic material and the thickness of the superconductor. And what you see behind is a 3D version. You'll see the substrate there. And this is a picture of one of the samples that we made. So we have the LASCO film on top a strip of iron. In this case, it has a width of 400 nanometers. This is the substrate, and these are the dimensions as we describe them here. So what do we believe is happening is that right underneath where the iron is, there will be a suppression of superconductivity. So this could be a weaker superconductor, depending upon the temperature. So we could tune that. We could make this more resistive and less resistive by cooling it away from the transition of the LASCO or coming closer to it. So there is a range of variability that we can use for different parameters. So we have the suppression of superconductivity directly underneath the iron strip, and finally, when we get some results, we apply for an international patent, and this is the classification. And this is on the creation of these this type of weak links and the devices that we can make with them. So to go further into the results, so I showed you this before in the case of 300 nanometers. So this looks promising. Then I would just show you how on this first quadrant for the current voltage plot, what are the IVs as a function of temperature? Okay, so we use the 1 micrometer area to determine the critical current. And then we plot this critical current as a function of temperature, and we have this type of curves. So besides the using the same or growing samples with iron, we use also other materials. We use, for example, the normal metal copper, and then we also measure a bridge without any materials on top. And these are the results I'm going to show you next. So in here, the results for the normalized temperature and normalized current for for example, a bridge that had nothing on top, it just behaved like if you compare this plot with the classical plot by Daly and Kleisner, which describe many types of high TC materials, Josephson junctions, especially of the type of S-N-S junctions, which is what we believe we have. We believe we have. Then, for nothing, we have this behavior, and then we have for the bridge is like there is no effect. But when we use the iron, then we do have some type of junction behavior. So the S-N-S junction provides easily control over the junction parameters, and so we can control easily the critical current and the normal resistance values. So this is again another indication that this structure that we created is a type of S-N-S junction. So we took this value, or took this one of the samples for, in this case, is the 300 nanometer sample. Is not here. Let me see. But anyhow, we vary the critical current as a function of magnetic field. We see a modulation, and then we can compare how this modulation in magnetic field will satisfy the equation for creating a quantum flux in between the area formed by the width of the superconductor multiplied by the width of the magnetic strip. So we do the calculation, and then we see effectively. So in this case, this is the result for the 300. So there is a discrepancy, but it's between the ballpark. So we see that we are satisfying this equation for the strip of 300 nanometers. And then we apply an AC signal to the sample. And in this case, we applied a 2 gigahertz sample, and then we see the appearance of Shapiro steps. So we were very happy to see so that everything was consistent to the creation of an S-N-S Josephson weak link with this method. So yeah, in this case, you can see that every step would be at around 4 microkelvin. So we have one here, microvolts. So we have one here, one step at 1 microvolt and 8, and so on. And then there are other steps, but we believe this is due to single, not a copper pair tunneling, but a single quasi-particle tunnel. And these can be explained because there might be a lot of just spin polarized quasi-particles by having the iron so close, and then being able to diffuse inside the region of the superconducting region. So there might be also the tunneling or the presence of just quasi-particles, just electrons that are inside the junction. after that, we created a squid. So again, this is the lask on top of the substrate, and then we have a bridge, and we place two strips of iron. In this case, these are 300 nanometers of iron, and then we take the current voltage characteristics, and then this would be how the resistivity or the resistance of the sample behaves as a function of temperature. But then when we apply magnetic field, of course, we see some oscillations. So in this case, both of these lines, or both of these junctions, contribute into the squid. So this is the results with this type of squid that we created using these junctions. And then we compare our results with a classical squid. In this case, Rogala measured squids created with IPCO. So these are at 80 kelvins. In our case, this is LASCO, so the critical temperature is much lower. So we place ourselves at 18 kelvins, and then we vary with the small magnet that we have there, the magnetic field, and then we see oscillations as well. And then the different values are for the different values that the fixed current that we place on the squid to see the modulation of that current. And then finally, sorry, let's go back. So we measured the height, the width of this voltage modulation. We measured each one of them, and then we plot that as a function of temperature. And then we find that if we want to have the most sensitivity, the maximum modulation will have to be around 24 Kelvin. That if I go back and just to show you where is that on the RT is into the superconducting, but very close to the. So let me just go back for a minute. So just keep in mind, so the maximum modulation or sensitivity of this squid, it would be around 24 kelvins. So if I go back, just to show you the RT. Oops. Actually, let me go like this. So 24 kelvins is somewhere around here. So if you can imagine what is happening inside the sample, the two areas next to each other, so there are two sections of the bridge, well, they will be already fully superconductor, but there will be the region in between that will have some resistivity. So there is a region that is a little bit strange, just the same way that we have at the first study that I showed you. So by placing here, some region has a resistance, but then the rest of the system is superconducting. So let me go back to where I was.
Luis, we are a little bit behind the schedule, so please.
I'm sorry?
Please try to finish in 3 minutes, okay?
Okay, I have 5 minutes to go.
Go ahead.
Yeah. So we're very happy to be able to have a high current junction weak link, high resistant weak link that we could use as a squid. So after finishing the study, I went to assist to work with the group of Andreas Schilling at the University of Zurich, the Institute of Physics, and then I carried out more studies with other materials. I don't think I had time to go over that, but I basically was assisting Holger Bartov in his measurements of single photon, and he was measuring a single photon detector made with niobium nitrile. So that was the next superconductor that I try to use this technique. So I use niobium nitrile and a ferromagnetic material to see if I could create a junction. But by the end of my study, so I tried the same model that I have here. I have a sapphire substrate. On top, we grow a very thin film of niobium nitrile, and I put nickel. And basically, now I did not see the same effect, unfortunately. So after finishing this work with them, I continue on my own with nano junctions, finding different combinations, different studies. So I am happy to tell you that we have come to the point where we understand what is happening. And although I don't have time to tell you this, and I'm also not able to come to Poland, I would have loved to be there to host the Monday poster session, the coffee, just to talk more about this. But I'd like you to welcome you to contact me. I will be present online. So just to summarize what I told you, I presented the results of fabrication and characterizing just some devices in other superconducting devices in many different materials, niobium over nickel, niobium over gold, niobium nitrile and nickel, and also LSCO and iron. And there is a material that I didn't show you, but I also try YBCO. And then, so we are at the point where we have filed for a provisional patent on all these discoveries and the many devices that we can make using these techniques. So thank you very much. Any questions? And thank you for staying to the end. Okay, let me stop this presentation. Stop sharing. So I guess I'm the last one in the group. Hello.
Okay, so Luis, yeah.
Yes.
I have a question in regards to tunable detectors of terahertz radiation.
Yes. Yes. So this is very interesting. Sorry, I didn't emphasize that part, but I believe on this curve over here, and let's see if I am sharing. Am I sharing my screen? Not yet. Share. Okay. So are you talking about this curve?
Well, it's a question of general nature. Do you have any applications of your tunable Josephson junctions for tunable detectors of electromagnetic radiation, and in particular in domain of terahertz frequencies?
Yes, this is one of our goals because as you can see here, since the ICRM voltage is so high, if you use the Josephson conversion, which is about 500 gigahertz per millivolt, so this will be on the region of terahertz. You know, if we can make a detection with this. When I was in Zurich, I created very high ICRN samples, but we did not have a source that will give us such a high frequency. There was a company in Switzerland called Alpes Lasers, and they were willing to collaborate with us, providing a terahertz lasers. But there was a difficulty because the terahertz laser itself, it needs to be cold, but it produces too much heat. So a new type of cryostat needed to be made. Oh, the measurements that I showed you for Switzerland, they were done on a PPM MS system, so it was very difficult to modify. But yeah, we believe that there is a strong possibility to make a detector in the terahertz regimes that can be used for maybe the microwave background measurement. So this would be one of my dreams, to collaborate with somebody to use these type of junctions as a detector on terahertz regime.